नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड NEET. This is our problem series for JEE Advanced. We are going to discuss the theory through problems. Hope this will be useful for all of you. I will request you to like and subscribe our channel. Question number 3. For a process which follow the equation PV to the power 3 is constant, the work done when 1 mole of ideal gas was taken from 1 atm to 2 root 2 atm starting from initial temperature of 300 Kelvin is. So these are the option given. This type of equation followed by an ideal gas is a polytropic process. If a gas is following PV to the power X, then it means that the ideal gas is participating in polytropic process. So let us revise some theory about polytropic process. An ideal gas participating in polytropic process means it will follow PV to the power X constant, where X is known as polytropic index. For a ideal gas participating in polytropic process, we can derive this equation of molar heat capacity of the gas, which is equal to heat capacity of the gas at constant volume, molar heat capacity at constant volume, plus R upon 1 minus X, where X is polytropic index. This is valid for all type of processes, though it is derived for polytropic process. So when we are discussing polytropic process, the value of X should not be equal to infinite or 0 or 1 or gamma, because if it is infinite, it is isochoric. If it is 0, it is isobaric. If it is isothermal, then it is X is equal to 1 here. So for all these values, already we have studied about these. So, but this formula we have derived when X is not equal to these values, but this formula is valid when X is equal to these values also. So apart from X is equal to these 4 values, if X is any other value, then also we can find out what is the molar heat capacity by using this, right? So for isochoric process, if we write that volume is constant, means X should be infinity, then we can say volume is constant. So for isochoric process, if X is equal to infinity in this equation, Cm is equal to Cv, and we are using it that for isochoric processes, Qv is equal to NCV delta T. For isobaric process, X is equal to 0. If you put X is equal to 0, pressure will be constant. And here we'll get Cm is equal to Cv plus R. Cv plus R is Cp. For isothermal process, the definition of isothermal is temperature remains constant, and the definition of molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a gas by 1 degree Celsius. So if the temperature is constant, if you provide infinite amount of heat, then also the temperature will not change. So molar heat capacity in isothermal process is equal to infinity. For adiabatic process, X is equal to gamma. So if I put here gamma, this is converted into minus Cv. So Cv and minus Cv is equal to 0. So Cm for an adiabatic process is equal to 0. And for an ideal gas participating in this, like PV to the power gamma constant, adiabatic reversible, we can write that work done is P2 V2 minus P1 V1 upon gamma minus 1. Same here, I can directly write that it is P2 V2 minus P1 V1 upon X minus 1, where X is polytropic index. And using ideal gas equation, P2 V2 is nRT2 and P1 V1 is nRT1. So nR is common. So this is T2 minus T1. So I can also write this is nR delta T upon X minus 1. Same way, P2 V2 P1 V1 upon gamma minus 1 right now. It must be a reversible process, because if we are writing this equation, it means that there must be some graph of this equation that is possible when the process is reversible. So like PV to the power gamma constant, here also I can write PV to the power X constant, or TV gamma minus 1. In place of gamma, I can write X, or P1 minus gamma T gamma. In place of that, I can write P1 minus X T to the power X is equal to constant. So now this ideal gas is participating in a polytropic process. So I can calculate the gas, 1 mole of ideal gas, not mentioning that which type of ideal gas it is. And they are asking that what is the work done. So here we can say that the pressure is increasing. So volume must be decreasing. It pressure is 1 atm to 2 root 2 atm. So this is the change in pressure. And initial temperature, they have mentioned initial temperature is equal to 300 Kelvin. And from here, I can calculate by using pressure volume relation. I can calculate what is the final temperature. So P final 1 minus gamma. In place of gamma, I should write X. Then T final to the power X is equal to P initial 1 minus X. T initial to the power X. Like adiabatic reversible, in place of gamma, I am using X. So now I can calculate what is the final temperature. So if I want to calculate what is the final temperature, I should write here that T final upon T initial to the power X is equal to P initial upon P final to the power 1 minus X. And on further simplification, I can write that T final is equal to T initial is 300 and this is equal to P initial upon P final to the power 1 minus X upon X. So if I put the value, this is 300 and initial and final pressure, I know that is equal to 1 by under root 8. 2 root 2 is under root 8. And this is equal to 1 minus X. The value of X here is 3. So 1 minus X means 1 minus 3 upon 3. So if I further simplify, I can write that this value is equal to 300 and this is equal to 2 to the power 1 upon 2 to the power 3 by 2. And on simplification, I'm getting this value is minus 2 by 3. So if we further simplify, I can write that this is equal to 300. And if I put this minus inside, it will go in numerator. And then we are getting this value as 2. So the final temperature is equal to 600 Kelvin. So final temperature T final is 600 Kelvin and T initial is 300 Kelvin. And we have to calculate work done when 1 mole of ideal gas was taken. So now I can apply the formula of work done in polytropic process, which can be written as P2V2. That can be written as P2V2 minus P1V1 is NR delta T. Delta T is T2 minus T1 upon X minus 1. So now if I put the value of N is equal to 1, R I will write R, and T2 minus T1 is equal to 300. Polytropic index is 3, so 3 minus 1 will be 2. So on simplification, I'm getting this value is equal to 150 R. So this is the work done in this process by the ideal gas. So answer will be B. Moving to question number 4. Calculate the maximum work done by the gas when pressure of 10 gram of hydrogen is reduced from 20 atm to 2 atm at constant temperature of 300 Kelvin. So the gas is participating in isothermal process. Now we have to decide that the process is isothermal reversible or isothermal irreversible, because pressure is decreasing. So it is known as it is expansion, but we have to find out that it is isothermal reversible expansion or isothermal irreversible expansion, that we have to decide. So in order to that, we are going to revise the theory regarding this. Suppose if I want to expand anything, right? So suppose here it is an ideal gas, and if I want to expand this ideal gas reversibly, then the difference between the driving force and opposing force will be very small. So at any point of time, this piston has infinite number of masses, and if the pressure of the gas is greater than the external pressure, here external pressure is equal to the pressure due to atmosphere plus pressure. Suppose N masses are there, identical masses are there. So N into pressure due to mass, 1 mass. So this is the external pressure. So what will happen that if the difference between the gas pressure and external pressure is very small, the piston will move slowly and then it will stop. Then again we'll remove a mass and the piston will again move slowly and then stop, right? So If the number of steps is infinite, we'll say that the process is reversible. So there is always maximum work done by the system because the opposition is maximum in case of reversible. So always the difference in pressure of the gas and external pressure is very small. So there is maximum opposition in reversible process. So in case of expansion, if word maximum is used, it is a common sense that it is a reversible process. Either it is isothermal or adiabatic. If they are using expansion and saying maximum work will be done when the process will be reversible. In the same way, in case of expansion, work is minimum means expansion is irreversible. When these masses are not there, only external pressure is equal to atmospheric pressure. So opposition will be minimum. So this piston will move fast, right? So in that case, we'll say that it is irreversible process. So one thing, in case of expansion, maximum means reversible and minimum means irreversible. In case of compression, it is reverse of that. Suppose if I want to compress something and I have to move from A position to B position, right? So if I'm moving A position to B position slowly, when I will add one mass and this piston will move down, then I will put another mass, then the piston will further move down and like that. So this process, when I move slowly, then the work done by the surrounding on the gas will be less because the gas surrounding is applying a little more pressure than what it is required to move. So in case of compression, when we are moving slowly, reversibly, then the work done by the surrounding on the system is minimum. If I want to move sudden from here to here, I have to apply the force here. Will from the very starting, I have to apply the force which is required at the last point. So I am doing more work. I am applying more force on this in order to move from A to B suddenly. Right. So in case of compression, when we are saying work maximum means it is irreversible and work minimum means it is reversible. So this is valid for isothermal, adiabatic, any process. Reversible in case of expansion is maximum. In case of expansion, minimum means irreversible. In case of compression, maximum means irreversible. In case of compression, minimum means reversible. Heat work and heat capacity, these are path variables. Otherwise, most of the variable which we study in thermodynamics are state variable. And most of the questions are based on that concept only. Entropy change, internal energy change, enthalpy change, Gibbs free energy change. These are state variables. So most of the concepts of thermochemistry and thermodynamics is based on that which is a state variable and which is path variable. Now moving to the question back. Here now I can say that they are asking about maximum work done by the gas when the pressure of 10 gram of hydrogen gas is reduced from this to this. So it is expansion and maximum work is used. It means that it is isothermal reversible expansion. They have given that temperature is constant. So isothermal, and from maximum, since it is expansion, we got that it is reversible. So we know that if an ideal gas is participating in isothermal reversible process, work done is equal to minus nRT ln V final upon V initial or P initial upon P final. So if I put the value over here, the number of moles of hydrogen gas, since the mass is given 10 gram, molar mass is 2, so this value is equal to 5. So this is 5. The value of R in joule we have to calculate. So 8.314. Temperature is 300 Kelvin. Ln P initial upon P final. So P initial upon P final is 10. So now if you go through these values, right? So in these values, you can find out that there is no sign mentioned here, right? So they have mentioned only the magnitude of work done, because all options have positive sign. In case of expansion, the work is done by the gas, so that should be positive. We are discussing here the magnitude of work. So now if I simplify, I can write that this value is equal to 1500, 8.314, and ln 10 is equal to 2.303. So without solving this question, we can say that if I divide this by 1000, so this will be 1.5 right? And if I multiply it by 16, so definitely it is in kilojoule, but greater than 2.872. And these options will not come because you can see the data. So without doing the calculation, I can say that the answer should be A. If you do the calculation, you are going to get the same thing. So the answer will be 28.72 kilojoule. So we can say that A will be the answer. Question number 5. 3 samples of same gas A, B, and C. So gas is same, but they are present in 3 different containers. Gamma value of the gas is given, have initially equal volume. Now the volume of each sample is doubled. The process is reversible adiabatic in A, isobaric for B, and isothermal for C. If the final pressure are equal for the 3 samples, the ratio of initial pressure are. So first we'll try to draw the graph for this whole process. I can draw here pressure versus volume axis. We can say that initially for all the gases, the volume is same. So I can write that this volume is V naught. And finally, the volume get doubled. So final volume is equal to 2 times of V naught. Now, for isobaric process, what is the name for isobaric process? That is for B, right? So isobaric process, when we are moving, and it is expansion because volume get double, but pressure is constant. Here, this is pressure and this is volume axis. So this is for isobaric process whose name will be B. So we are moving from here to here. This is the initial state. So initial and final pressure will be same. Now, for gas A, the process is reversible and adiabatic. So it is expansion. So definitely we are moving from somewhere here. And final pressure is going to be same. So this is for A process. A process is for adiabatic, reversible. And for adiabatic reversible, the slope will be change in y upon change in x. So this height will be more if I compare with isothermal process. For isothermal process, if I try to draw the graph, this should be the graph. The initial volume is same and the final pressure is same. So this is a graph C, and this is for isothermal process. So this is for isothermal process, and these are the initial pressures, right? So we can, without solving, I can say that in case of A process, the pressure is highest, and then in case of C, and the pressure will be lowest in case of isobaric process, right? So now I can say that the initial pressure here is Pi, and Pi is equal to P final in this case, in case of isobaric process, that is the B process. Now, in case of isothermal process, P1 V1 is equal to P2 V2. Volume get doubled. It means that the initial pressure was 2 times the final pressure. So I can also say that the initial pressure in case of C, isothermal process, is 2 times the final pressure. For adiabatic process, I can write pressure volume relation PV to the power gamma constant. Initial pressure I have to calculate. Initial volume is V naught. PV in case of A process, since it is adiabatic reversible, I can say that PV to the power gamma is constant, right? So here, if I simplify this, I'm getting that P initial is equal to 2 root 2 times of P final. So this is the value 2 root 2 times of P final. Now we have to write the ratio of pressure in case of A process, initial pressure, then in case of B process, initial, and then in case of C process, initial pressure. So in A, initial pressure is 2 root 2 times of final pressure. P final will cancel out. In case of B, this is equal to 1, and in case of C, this is equal to 2. So the ratio is 2 root 2 is to 1 is to 2. From there, we are getting the answer A. A will be the answer. Question number 6. A liquid confined inside an adiabatic container is suddenly taken from state 1 to state 2 by single stage process as shown. Then delta H is. So most of the student don't read that what is the system, right? Here the system is liquid, it is not gas. So it is liquid. So for a liquid confined in this adiabatic container, I can apply first law of thermodynamics. I can write that Q is 0, so delta U is equal to W. For any system, W, work done in irreversible process, is equal to minus times of P external, V final minus V initial. They have not given anything about the external pressure. It means that external pressure is equal to the final pressure of the system. The final pressure of the system is P naught. So I can write P naught, and volume change I can write that is 4 V naught minus V naught is 3 times of V naught. So this is the change in internal energy or work done, which is equal to minus times of P naught V naught. And then we can write that delta H is equal to delta U. This is valid for solid, liquid, gas, all, right? So delta H is equal to delta U, P final, V final minus P initial, V initial. So if I put the value, delta U is equal to minus 3 times of P naught V naught, and P final V final is 4 times of P naught V naught, and P initial V initial is 2 times of P naught V naught. So on simplification, we are getting this value is equal to minus times of P naught V naught. So we are getting B as the answer. The answer of this question will be B.